Hello everyone. Today we'll be studying about inert pair effect. Okay. So before starting the inert pair effect, let's recall the screening effect that we have covered in our last video. Okay. So what is screening effect? I told you there that screening effect is the reduction in the force of attraction that is experienced between nucleus and your valence electron due to the presence of inner electrons. This force of attraction that is between your nucleus and valence electron, this reduces due to the presence of valence electron. This is called screening effect. There I also told you more inner electrons or more core electrons, more will be the shielding effect. Okay. So we have studied this in the last video. You can go and check it out there. It's there in the channel. Okay. So order of shielding effect. If we write the order of shielding effect of the orbitals, shielding effect. So this is S, P, D, and F. Okay, S, P, D, F. S has more shielding effect and F has less shielding effect. Now let's come on the topic that is inert pair effect that we have to cover today. Okay, so if okay, before inert pair effect, let's start, because this inert pair effect deals with the oxidation state. We'll see how oxidation state varies when we go down the group. Okay, so let me rub this. This we have, you have, I hope you have noted it down. Okay, so oxidation state, oxidation state. Maximum oxidation state of any group, maximum oxidation state of any group is the total number of valence electron, maximum electrons that it can lose. Okay, so if we'll talk about the maximum oxidation state of group 13, 14 and 15, they have valence electron. Let me change the color. This group has 3 valence electron, this group has 4 valence electron, and this group has 5 valence electron. Okay, so if we'll talk about the maximum oxidation state, so maximum oxidation state for group 13 will be +3, for group 14 it will be +4, and group 15 it will be +5. Okay, maximum oxidation state I'm talking about. So according to this concept, if we'll mark the oxidation state of the group, so we'll say that this boron will show +3, aluminum will show +3, gallium will show +3, indium will show +3, and thallium will show +3. Okay, likewise, the carbon will show +4, silicon will show plus. All these elements in the same group will show +4. Here, the maximum oxidation state is 5 because they have 5 valence electron in their orbital. Okay. So till now, as per our knowledge, what we know about the maximum oxidation state and oxidation state, we have seen that the oxidation state should be this. But it's not like if we'll go down the group, you will see key here oxidation state is not +3 here, it's not +2 here, it's not +5. Okay, it decreases. Now let's understand why this happens. Okay, what is the reason behind this? So when this is your second period, this is your third period, this is your fourth period, this is your fifth period, this is your sixth period. Okay, here. When we go from fifth to sixth period, fifth to sixth period, your lanthanide elements involved. Lanthanoid elements are involved. Okay, lanthanides elements are involved. Your lanthanide elements are involved, and we know that in lanthanide elements the last electron goes in f orbitals. Okay, last electron goes in f orbitals. In the starting of this lecture, I have told you order of shielding effect. Or order of shielding effect, if you remember, what was it? It was S, P, D, and F. Okay, F has your poor shielding effect. So here your electrons, F orbitals are involved, or electrons goes into the F orbitals. So shielding will be poor, and we know that shielding will be poor. And poor shielding effect means Z effective increases or more force of attraction, or you can say more nuclear force. More nuclear force. Okay, that means your valence electrons will be pulled to by the nucleus more strongly. Okay, now let's see what will happen. This much we have understood. Okay, so let's take this boron, and the valence electron will be 2s2 2p1 here, and in case of thallium it will be 6s2 6p1. Okay, because it's of sixth period. So this is I'm talking about boron. Okay, here boron has 2 electrons here, 1 electron here. Similarly, we'll talk about thallium. Okay, this is here thallium. 2 electrons and 1 electron. This is 6s2 6p1. Okay, so we have seen ki as we go down the group, okay, as we go down the group, the shielding effect increases. But here the f orbitals are involved, and due to the involvement of f orbitals, because we have seen the f orbitals, a shielding effect is very less. Okay, so due to the poor shielding effect, there will be more nuclear force. This nucleus will apply more force of attraction on this valence electrons. It will apply on both, on 6s and 6p. But we know that 6s orbitals are more closer. Okay, so more force of attraction will be applied on 6s, and comparatively less will be applied on the 6p. So in the case of thallium, if it has to lose electrons, the 6s orbitals, this and this, the 6s orbital electrons are highly attracted by the nucleus. The force of attraction is very high, so it will be very difficult, or it won't be able to give its electron. Okay, so here thallium will just lose 1 electron. That's why its oxidation state is +1. But and in the case of boron, there is no such restriction, so here it can lose 3 electrons and it will be +3. Okay, so this is due to your inert pair effect, because due to inert pair effect, if you see this two electrons becomes inert, and they are not shared now, and the 2 electron makes a pair. 2 electron makes a pair. That's why it's called inert pair effect. Means you are making a pair. You are making a pair of electron inert for not participating in bonding, or these electrons are inert and they can't be shared. Okay, so this is your inert pair effect. Okay, so if you you may write down the consequence of inert pair effect. Okay, let me wrap this. I hope this is clear with you all. Okay, so you may write it down that due to inert pair effect, to inert pair effect, the oxidation state of the sixth period element decreases by 2 units. Okay, you must remember this. So now if you see here, if you're in group 13, if this boron shows +3, thallium will show +1, decrease by 2. So carbon will show +2. So if carbon will have +4, so lead will show +2. Okay, similarly, if we'll see in this case, if it's +5, it will be +3. Okay, so this is your inert pair effect. We have seen, due to inert pair effect, your oxidation state of the sixth period, okay, decreases by unit. If we'll talk about this bismuth, this will show +5 also. +5 oxidation state will also be shown by bismuth, but +3 is more stable. This is more stable. Okay, and why? This is due to the inert pair effect. Okay, so now let's come on the definition. It says the inert pair effect is the tendency of two electrons. Which two electrons? S orbitals electron. We have seen here. Let's consider if we'll see thallium. So in case of thallium, it was 6s2, it is 6p. Okay, so this electrons, this two electrons becomes inert. Okay, so it is saying the inert pair effect is the tendency of two electrons in the outermost orbit, atomic s orbital, this is s atomic orbital, to remain unshared in compounds of the post transition metals. Post transition metal means, because here your d block elements will come, and d block elements are called transition metals, and these are coming just next to the transition metals. That's why it's called post transition metals. Okay, so inert pair effect was basically your effect in which your ns orbital, outermost ns orbitals electron, two electrons, they become inert and they do not participate in any bonding, and they are not shared by the electron. That's why it's called inert pair effect. And due to inert pair effect, your oxidation state decreases by 2, okay, in the 6th period. I hope this is clear with you. If you have any doubt regarding this, you may comment down below, and I'll try to solve your queries. Thank you so much for watching.